Hello, welcome to numerical ship and offshore hydrodynamics. So, today we are having the lecture 26. Now, in this lecture we are going to again discuss about the how I integrate the Rankine part of the Green's function. Now, in last class we have discussed that how we can integrate analytically when source point and then field point are very close to each other. Now, today we need to discuss about the how do I integrate over the quadrilateral panel. Now, if you remember I said in the last class that since it is like a rectangular hyperbola. So, therefore, a larger period of the space we are going to do the quadrilateral, I mean that 2 point Gauss quadrature rule. So, today actually let us discuss about the how integrate over the quadrilateral panel using 2 point Gauss quadrature rule. Then you can actually take a homework to extend that theory for the 3 by 3 Gauss quadrature rule. Okay. And this is the keyword that you are going to type to get this lecture. Okay. Now, let us start. Now, here if you look at this the ship model and it is a wiggly hull right. Then you can see that the point that panel the corner point at p I x I y I z I, it is a point on a surface. So, it is really not like a orthogonal plane, it is not along that x I y I and z is constant, then or y I z I x is constant, or maybe y I z I x I constant. I mean not like that, it is all varings, right. So, essentially it is a 3D point, right. Now, if you know that Gauss quadrature rule, this we have to have a 2D point, right, because the Gauss quadrature rule says its integration from -1 to +1 for the x direction and -1 to +1 for the y direction. So, now, so that what is the basic philosophy is as follows. I have now this R3 domain, this coordinate is 3 dimensional coordinate of course, right. I mean when I say the 3 dimension, the is a 3 dimensional point, right. So, I need to first transfer this 3 dimensional point to the 2 dimensional quadrilateral surface. So, both are quadrilateral, but it is inclined plane and then it is a 2D plane. Now, there are many ways to do that. You can do some angle operation from this side and that side. So, this is one way you can change that to that, but there are several other approaches also available. So, and most of the time, not most of the time, in very I would say that very few time, like not necessarily that all these 4 points lie in a same plane. Now, everybody knows that with respect to 3 point I can define a plane, not necessarily that 4th point should lie on that plane. Now, here in this scheme what we are going to do that even if it is so, actually we can take a projection so that all the 4 equivalent, all the 4 point lie in a same plane, that we make sure, and we will see how we are going to do this. Now, once it is possible to get this R3 point into the map to the R2, then again we are using another mapping from R2 to this -1 +1 this square map, because this Gauss quadrature rule should be that limit should be -1 to +1 for x and then -1 to the +1 for the y, and we can call this a natural coordinate system. Now, so what we are doing here, from this P3 3 dimensional point, we are going to have let us say 2 dimensional global coordinate system u and v. Now, from this 2 dimensional global coordinate system, again we map back to the natural coordinate system that we can call is a minus 1 to plus 1 for the this horizontal direction and minus 1 to plus 1 for the vertical direction, right. And then after doing this we are going to do this integration, right. And then of course, that that limit, as I said that this is the more tricky part, like what would be the integration limit in the global coordinate system, that we really do not know. So, therefore, but however, in natural coordinate system of course, it is integration from minus 1 to plus 1 into the functional value of course, f zeta into Jacobian d zeta d eta. So, this d j d eta. So, this this it is known to everybody, right. Now, let us try to figure out how we can do all these things and then get the value for integration of 1 upon r and integration of r dot n by r cube. Okay. Now, here, so first let us try to see that how from this the 3 dimensional point p 1, p 2, p 3 and p 4 we can get the equivalent 2 dimensional point. Okay. Now, here we define one vector along this horizontal axis, you can see it is p 2 minus p 1 by mod of p 2 minus, so is a unit vector along x, and then we can find out that unit vector along it is a temporary, like so what we are going to define, we are going to define one is along p 1 p 2, another vector is along p 1 p 3. Now, if I take a cross product, definitely I am getting the normal. So, V n is nothing but the normal to the vector which is V x and V y t. So, it is a normal. Now, here I understand that V x and V n both are perpendicular to each other. However, V x and V y t is not perpendicular to each other, right. So, but what I need is I need a local coordinate system which is I mean all these axes should be perpendicular to each other. So, therefore, I redefine this V y t into V y by having this V n cross V x. By doing this, what actually we did that, now I am having a local coordinate system which is V x, V y and V n, right. So, this is the first thing that we are going to do. When I have a panel, with respect to that I am having the mutually 3 perpendicular vector, one is along the horizontal direction, one is along the transverse direction and one is the normal to this plane, right. So, this is the first job that we are going to do. So, when we are having it, now let us then it is very easy to get the corresponding 2 dimensional point. Let us see how we are going to do that. Now, then again I define the 4 vector which is the distance from the point. So, so therefore, I can define one called the V C G I, which is the distance from the C G is a 3 dimensional point. So, it is C G minus P 1, then you can get V G 1, then I can get C G minus P 2, you can get V G 2, I can get C G minus P 3, I will get V G 3 and then I can get C G minus P 4. So, I get V G 4, right. So, this I do, and then my U I is nothing but the dot product of V G I with the V x, right. Now, this is because I am taking this component of this along this horizontal axis. So, then this U I is basically the point on the x coordinate system. So, so now in my local coordinate system V x, V y and V n, now U I is falling on this local coordinate along the line V x, because I am taking this component along the V x. Similarly, the similar way I can take the, if I take a dot product with the V y, and now remember this V y also the mutually perpendicular axis. So, therefore, V I is again along this axis V y, right. So, this is how I am transferring my, and also the local coordinate, because it is a local coordinate system, the another component definitely I am going to get 0, take 0. So, so this is the point that U I and V I, which is nothing but the, on that particular point, this which is P 1, P 2, P 3, P 4 would in the surface. Now, I transfer that to the U 1 V 1, U 2 V 2, U 3 V 3 and U 4 V 4 V 4, right, and where it is on the local coordinate system, which is U and V, right, fine. Now, here, now what actually, let us see that what actually we did and what is more required to be done as follows. Now, what we did as follows. Now, I have let us take a inclined plane like this. Now, with respect to this, this is my point P, right. Now, okay, let us not this, let us, okay, let us do it again. Suppose this is my that inclined panel, right, and it is inclined on both sides. Let us say this is the angle alpha, and also if I make a transverse direction somewhere here. So, this angle also it is, let us say beta, something like this. So, it is a 3 dimensional point. So, it is inclined this way and also it is tilted this way. So, now here, now with respect to that I have the point P over here, right, and then now if I change, now essentially when I am doing the dot product, what I am doing is I am actually incorporating the angles, right. So, I change the orientation. So, I make this as a flat panel like this and something like this is the idea, right. So, I have a inclined in a 3 dimensional surface point, let us take this way, this one, and now if I apply this rotation, then I can get this panel with like this. Now, maybe in this horizontal axis again I have the beta. Now, if I apply this beta angle also, so finally, it is lying on my UV plane, right. So, lying on my this this plane, let us call it UV, and in fact, we can call this a Vx and this one in along like Vy, mutually perpendicular. Now, what happened to the point P now? Because P must gone through all this coordinate transformation, so that this distance, the normal distance, let us say d, that must be that must be invariant under all such transformation law. So, therefore, it is not only shifting the panel from the 3 dimensional to the 2 dimensional, at the same time I need to shift the point P from here to here also, right. So, let us see how we do that. Now, here again it is again very simple that x p, now what is P is the source point, right. So, then actually I can define that x p is nothing but the, now here it is the distance, the x component is nothing but that the distance, the horizon. So, it is P of x minus C g of x. So, that is the x component of that vector, right, and then that vector actually I multiply by the V x, I mean the dot product of V x, then y p again similar way, that P minus C g is a vector and then it is dot product by y, and then the Z p is again this P minus C g, but now I am having the dot product with the normal. Now, why I said plus minus depending on the situation, with when taking the positive upward like inward to the fluid, outward to the body, or maybe the inward to the body, outward the fluid. I mean that is based on that all the formulation can change. So, therefore, it is your choice how you define your normal, how you write that integral equation, right. You have to adjust the sign plus minus everywhere. So, here that is why I keep as plus minus p minus C g dot V n. Now, you see after applying all this thing, what I do is this point P 1, P 2, P 3, now I have a equivalent point on U 1 V 1, U 2 V 2, U 3 V 3 and U 4 V 4. And also remember, when you have a coordinate transformation, definitely there is a possibility that that area might change, right. But if you do this vector application, you can check that area remain invariant, right. So, therefore, you really do not need to introduce any kind of Jacobian here. Okay. Now, what is the definition of Jacobian, why the Jacobian is required, definitely we are going to discuss today only later on. But at this point, what I am trying to say is as follows: if you apply this coordinate transformation, then that area. So, like okay, let us go back here again. What I say is as follows: in case of this the global 3D point, that may be your the quadrilateral, that P 1, P 2 and P 3 and P 4, and let us say area is A star or maybe A star. Okay. And then you do this coordinate transformation, and you can now having it is on the flat surface along this is here V x and maybe along this in V y, and then you have let us say U 1 V 1, U 2 V 2, U 3 V 3 and then U 4 V 4, and if the area is A star star. So, my point is this A star is equal to A star star. So, this transformation actually that area is invariant under this transformation. So, that is the whole point I want to make. Okay. Now, having said that, it is this area is invariant under this transformation. So, now I am having the 2 dimensional points, that U 1 V 1, U 2 V 2, U 3 V 3 and U 4 V 4. Then with this respect to this, now I need a serious coordinate mapping from here to the our natural coordinate system, which is -1, -1, 1 minus 1, 1 1 and -1 comma 1 here, right. So, now how I do that? Now, if you do this isoparametric things in finite element, I mean if you have those courses, then definitely you know that how we are going to do this, but in case you do not have. So, I am just trying to just give you some idea like how we can implement that and how we can do the integration. Okay. Now, here in general any point u can be defined as the sum of u 1 into n I, which is this n I is nothing but a shape function. Now, what is shape function and what is its importance, everything that is definitely is a part of the study. We are not interested here at this point. However, like if you say that this isoparametric things, material and everything there. So, is a very standard way to define a point on this transfer from this global coordinate, which is u 1 v 1 u 2 v 2 I mean u v system to the natural system through this shape function. Now, what are those shape function? Then what is the property of this shape function? Now, here the shape functions, this property is that at the node actually I am interested that shape function, it takes the value 1 there, and then in other 3 point the value becomes 0. So, just like let us say for n 1. Now, if I do this if I do this point, now it is, let us take, it is this node 1, it is a node 2, let us take this is node 3 and let us say node 4. Then in n 1 at node 1 it takes the value 1, in other situation it takes the value 0. So, if I try to draw a the plot of n 1, this curve, this should be something like this value, something like this. It is here it is 1 and in all points it is 0, and then some way it is going from 0 to 1. Now, this what is the expression for the n 1 in that case? Can you say that, like in this node? So, that means at minus 1 comma minus 1 it takes the value 1, and in all other point it takes the value 0. So, what would be the node function n 1? Remember, I said it is at minus 1 it takes the value 1, or in all other point it takes the value 0. So, it is very easy, you can, so there is only unique way you can do that, it should be 1 minus xi into 1 minus eta. Now, if you do that, you can check that in case of, if you put the value 1 comma minus 1 or minus 1 comma 1 or take 1 comma 1, then you can see that all the points this value becomes 0, and if you take this minus 1 and minus 1, then you can say that value of n 1 become 1, right. Now, using this understanding, this is enough for doing our job. Okay. We really do not need more theory just to do this integration of 1 upon r for using this quadrilateral panel, this is enough. Now, if I do this, then definitely I understand this n 1 equal to 1 upon 4 1 minus xi into 1 minus eta. Then if I use the same logic, so definitely for n 2 the value should be that 1 upon 4 1 plus xi into 1 minus eta, I am talking about this point. Right. Now, in n 3 it should be 1 plus xi into 1 plus eta, because I am talking about this point, and now in n 4 it should be 1 by xi into 1 plus eta. Now, once we have this shape function, so definitely I am ready to define that any point on the natural coordinate system using this coordinate, this law, using this result. Now, I am ready to define the point on u and v on the natural coordinate system. Okay. Fine. Now, in order to do the integration, that I need to find out what is the Jacobian. Now, what is Jacobian? You see here, if you look at this integration scheme in before, here we can see that it is the integration, we have the some term which is mod of j, and this is nothing but the Jacobian. Now, what is the Jacobian and why it is used? So, let us try to discuss why it is important to introduce the Jacobian here. If you remember, I just discussed that when you do this previous transformation from this 3-dimensional coordinate into this 2-dimensional UV domain, I mentioned that it preserves the area, right. So, area does not change. So, therefore, the ratio of the two area equal to 1. So, then actually we really do not need any Jacobian, because Jacobian exactly doing the same thing. Like now, when you do the coordinate transformation, it is possible that area is not invariant. So, therefore, you need to multiply the Jacobian to adjust the area itself. Now, unknowingly during your school days, you do any coordinate transformation for one dimensional thing. For example, let me give you this thing. Let us say if you try to do integration some a to b, some integration I, and then you are try to do it is 1 minus x square into dx. Let us say you are try to perform this integration. So, what you do is here, if you remember, you put that you take x equal to some cos of t, and then what you do is you do dx by dt, which is nothing but minus sin of t. Now, here then you change this I from x to t and you change the limit. Now, earlier the limit is function of, so now it is changes to the t. So, now this a is now function of t, and then the b also then the function of t, right, and then what you do is you changes this the function of f x. Now, this function of f x also you change to some function of t, and then you multiply the Jacobian, which is dx by dt, that is called the Jacobian, which is minus of sin t, and then you integrate in the domain t. So, that is what we are doing. Now, if you look at this, what is dx? Dx nothing but the length, and what is dt? Dt also nothing but the length. So, what I am doing here, I am multiplying this coordinate system with respect to keeping the area in case of one dimensional, which is the length. So, the ratio of this to length we call that is the Jacobian. So, this is the physical explanation of the what is the Jacobian. Now, this is very important, we need to do that. So, now how we are going to do over here? So, now here as I said this integration limit is unknown to me for this this uv domain. However, in natural coordinate system is definitely minus 1 to plus 1, but then there should be some area should be should be multiplied with the area, because area may be same, may not be same, I really do not know. Now, here this is how we do the Jacobian, and this is the standard formula. I mean everybody know about this is the standard formula of the Jacobian. Now, how to apply over here? Now, here I know this is by definition for u, it is u I n I and v is v I n I. So, I know this definition, right. Then this this Jacobian is nothing but you just replace by u over there. So, it turns out to be u I into summation I equal to 1 to 4 del n I by del xi, and similarly the other 4, right. This is how I can find out my Jacobian. Now, this Jacobian I know how to, is a determinant of this, of course, is the Jacobian, I mean mod of Jacobian is a determinant. So, now once I know this, so now you can see this everything is ready for me, minus 1 to plus 1 the limit I know, minus 1 to plus 1 limit for eta, that also I know. Jacobian now I know, because I know the shape function. So, therefore, the differential with respect to xi and differential with respect to eta, that also I know. I can add everything and I know how to get the value for the 2 by 2 the determinant, right. It is if we call is a 1, it is a 2, it is a 3, it is a 4, then a 1 a 4 minus a 2 a 3, that everybody understand, right. Okay. So, now the integration scheme, the 2 point Gauss quadrature scheme, actually it is this turns out to be I equal to 1 to 2, j equal to 1 to 2, w I, w j, f I j multiplied by the Jacobian. So, therefore, it is a standard scheme for everywhere, any rule is a quadrature rule, it is a other integration technique, trapezium, everywhere you have a functional value, you have a weight function, you multiply this, right. So, now here what is w I and w j for our case, which is called the weight function. Now, in case of minus 1 to in case of this Gauss quadrature rule, 2 point Gauss quadrature rule, this weight function is 1. So, fine. So, there is nothing wrong with this. So, it is 1 simple, and also xi I and eta j, those are the Gauss point, but this Gauss point in this minus 1 plus 1. So, what is that? This is also very well known, you can get it from the geo of the Legendre polynomial. We are really not going to discuss all this mathematical thing. Okay. So, here we are just use those results and try to do this integration. So, here it is again plus minus 1 over root 3 plus. So, this now I know everything over here. I know in the integration or the weight function the value 1 and 1. I know all these Gauss points now, it is minus 1 by root 3, minus 1 by root 3, then plus 1 by root 3, minus 1 by root 3, then plus 1 by root 3, plus 1 by root 3 and then plus 1 by root minus 1 by root 3 into plus 1 by root 3. So, these are the 4 points I am getting, okay. And then simply I use this and I can get the value for this integration. Now, only thing we have not yet discussed, which is the functional values. What are the functional value over here? Now, you know this we have to two integration, one is g, which is 1 upon r. Now, this 1 upon r is nothing but the distance from this source point, which is x p, y p, z p, to the field point, which is xi eta 0. Now, here in Gauss quadrature rule, the 4 Gauss point is nothing but the source point, right, fine. And then that another functional value f zeta xi eta, which is grad g dot n q, and that is nothing but r dot n divided by mod of r cube. That is also you know, where the x p, y p, z p are the source point and xi eta 0 is my sorry, x p, y p, z p are the field point and xi eta 0 is nothing but my source point. And what is the r? R is a vector which is x p minus xi, y p minus eta and z p. So, now I know my functional value. So, what I need to do is very simple. I have the 4 Gauss point, and each Gauss point I am trying to find out what is the value for g and what is the value for grad g dot n, right. And then I apply and in this previously summation, in previous summation form I put these values and and also those point also I need to find out the Jacobian, right. Now, here you can say you have a 4 Jacobian point, right. So, then what is the 4 Jacobian point? Now, if you do this differentiation, then it is a function of again xi and eta, and in this xi and eta you have to if you put the value for xi I eta I, then definitely you are getting a number, right. So, from this Jacobian also we can get the number, because it is del n del xi, which is nothing but a function of eta, right. And this eta, if I put the value of eta I and then again del n del eta, we get the function of xi. In that function I take the value of xi, and similarly del n del xi and del n del eta for V I also I am getting. So, at the end in each point I am getting the value for the Jacobian, because at each point I know what exactly my eta I and xi I need to substitute in this and I get the value for Jacobian. So, that Jacobian value we are going to apply over here for each Gauss point. Each Gauss point I am trying to find out what is my functional values, and weight function is of course 1. So, therefore, I can get the integration, right. So, now this is how actually we are performing the integration for 2-point Gauss quadrature rule for the quadrilateral panel. And now it is I would like to give a homework, try to extend this theory for the 3-point Gauss quadrature rule. Okay. So, let us stop today. Thank you very much.